Okay, so let's take a look at these projectile motion notes here. There we go. So to start off with, we have the definition of what is a projectile. So what is a projectile? It says right here, it's any object launched into the air and acts only under the force of gravity. But it says it also has horizontal motion. So pretty much anything that flies through the air under the influence of gravity only is a projectile. Okay? So if you throw a rock through the air, is that a projectile? Yes. What about a water balloon? Is a water balloon a projectile? What if I throw this chair? Is that chair a projectile then? Yeah. What if I throw this desk? Is that desk a projectile? What if I throw one of you? Are you a projectile? What if a plane flies there? Is that a projectile? No, a plane is not a projectile. Because a plane has engines that are pushing it, and therefore it has another force, right? So as long as the plane's engines are up and running, it's not a projectile. Does that make sense? Because it's something that flies in the air under the influence of gravity only. So in here, we're specifically talking about things that also have like an X horizontal motion. So, something that's propelled forward. But a plane, if a plane's engine's turned off, would it be a projectile then? Yes, it would be a projectile in that case, specifically because then it would, quote, fall like a rock. So here it gives you some examples. Also notice that some things like bullets fired from a gun are projectiles. And a lot of people want to say, well, but it was fired out of the gun. Like, yes, a ball can be fired out of your hand. But once it leaves your hand or the gun, then it's no longer being pushed, right? Then it's just a projectile flying through the air under the influence of gravity only. So we define this first because that's what we're studying today, is how projectiles work. So here, this gives you the path of projectile, and it talks about that projectiles here have a parabolic trajectory. So projectiles follow this path through the air, which ends up looking like a parabola, right? And that path is called the trajectory of the projectile. I'm not going to quiz you all so much on those words, but again, you have to know what those words mean. Like if I use them in the problem, like the trajectory, blah, 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 you have to go, okay, I know what that is. It's simply the path it moves along. So it's anything. So here you can see like the soccer ball being kicked, the motorcycle flying through the air. The biggest thing you have to learn in this section is the fact that the X and Y stuff, that what happens in the X direction or horizontally, doesn't affect what happens in the vertical direction. Now, looking at these projectiles, you see this nice parabolic curve, or when you throw something through the air, you see a nice parabolic curve, and it looks like the X and Y stuff are affecting each other, but they're not, right? The X motion is essentially constant, like we don't have any air resistance or anything. There's no acceleration, X in the horizontal direction. Because there's no acceleration in the horizontal direction, the motion is constant, right? It's just like a ball just constantly rolling along the ground. That every moment you look at it, it's going to cover the same distance in the same amount of time. Then vertically, we have accelerated motion because of gravity. Now they look like they're connected because you only have one object, and in the end you only have say one actual velocity. But we can use vectors, like we talked about, and we can break them into pieces. Now for you guys, I want you guys to understand that, number one, you have everything you need already to do projectiles, as complicated as they could ever possibly be. But number two, since this is, just a regular physics class, I'm not going to give you some super complicated problems, okay? Because the only thing that's going to do is just make you guys do more math, okay? So in this class, instead of firing projectiles up in the air or shooting them off a cliff or something, we're only going to have horizontally fired projectiles. balance, which means it's like a ball rolling off a table. You drive your car off a cliff, or you run and jump from one building to another. It's horizontally fired projectiles. That would make things a lot simpler, but I want you guys to be aware that we've given you the tools to handle everything. But again, it's one of those things that if I give you a bigger problem, then it's not going to be these concepts that mess you up, it's going to be the math. So we're not going to focus on getting too math heavy here. So here, this kind of talks about how we want to separate your X stuff from your Y stuff. So in the horizontal motion, since there is no acceleration, we just have constant motion. And so this right here, this Vx equation, is actually the very first equation I gave you this year that I said, your average velocity is your change in displacement or your change in time. There it is. And then in the vertical direction, we end up with a couple more equations. So this is a simplification of our V equals V naught plus AT. And then remember that big displacement equation, that Y equals Y naught plus V naught T, blah, blah. That's this guy right here. So one of the biggest things about projectiles is this is probably the hardest thing that you're going to encounter this entire year. The main reason why it's so difficult is because I can ask you one projectile motion question, and I can literally cover every single topic that we've gone over this year in one question. And I don't even have to try. So, like, that's what I'm trying to point out here. Like, this is the very first thing that we learned. And the very last thing we learned was how to break apart, vectors and add them together. So all of that is contained in projectiles. So the good news is this is probably the hardest thing that we're going to do all year. The bad news is, well, it's probably the hardest thing we're going to do all year. So you got to pay attention here. And so one of the biggest keys is to separate your information. So here it says your horizontal velocity, we call that Vx. We also have like a vertical velocity, Vy. We have horizontal displacement, which we call the range. We have vertical displacement, which we call the height. We have acceleration due to gravity, which is always in the y direction, which we're going to round to 10. And then time. Now notice that time doesn't have a subscript. It doesn't say, time x or time y, because time is not a vector. It's a scalar. Because it's a scalar, it doesn't have a direction. So out of all of the information up here, the most important piece of information is going to be time, because time is the only thing you can use for both x and y. Sometimes I give you the time. Sometimes I don't. If I don't give you the time, and you're like, I don't know what to do, that's a real good first step, is to find the time. Okay? So, here, this just talks more about this, and if you were to break these things apart, you could see that the horizontal velocity stays the same, whereas the vertical gets accelerated downward by gravity. Here, this is a PhET sim. It's a very useful one. I recommend that you play around with it. It's obviously capable of doing a lot more than I'm requiring of you guys. Like I said, I'm going to require that you guys just do horizontally fired projectiles. So here, for instance, I can just hit this button and boom, it fires. Whereas, like, I can raise it up and then I can fire it again, and it goes further. I didn't change the initial speed or anything like that. If I come back down here, I can change the initial speed and fire it, and you'll notice that it doesn't go as far. Or give it more speed and it goes further. But notice every single time it's a parabolic trajectory, right? So I recommend playing around with this, kind of getting familiar with it. If you want to look at the vectors, it has a thing here so that you can see the vectors as it goes along. It might be too fast, so we have like a slow button. You can pause it as it goes. You can look at the acceleration and all of these things. If you want to get fancy, you can change it to, instead of firing pumpkins, now it's firing a piano. It's the same thing, because it doesn't matter what you fire, because it's a projectile. So that's a useful tool to look at different things being fired without actually having to leave your bedroom. So here, this gives us a thought experiment. It says, pretend like you have a group of survivors on an island in the middle of the ocean. And you're flying a plane and you wish to drop them some supplies. Well, obviously the island would be in front of you. You haven't gotten there yet. When do you drop the supplies? Do you drop them before you get there? Right when you're above the island or after you pass the island? Well, if you think about it, when the plane is flying, everything in the plane would have to have the same speed as the plane. If it didn't, it wouldn't be in the plane for very long. So the plane is flying along and you have the supply drop that you're going to drop. It has the same speed as the plane. And when you let it go, it's going to fall because of gravity. So from the plane's perspective, that's this first picture here, this A part of your picture. From the plane's perspective, the crate gets smaller, it's just falling down, but it stays right with the plane. If you look at the side shot here, part B, you can see that it falls down, but it's also going forward with the plane because it has that same velocity. Because again, your horizontal component is independent of your vertical component. Now, what's interesting about this is we're not talking about air resistance and all that stuff. And I told you guys, as long as this thing is shaped well or not moving very fast, you could ignore air resistance. But how well does this work in real life? Well, there's a little clip here that demonstrates that. I'm going to mute this because the sound is really useless. It's already muted. So here, you can't actually see anything yet because it's inside of this aircraft. So they have to wait for them to open the doors. There we go. Now here, this is actually the interior of a B-52. And it's trying to drop these bombs here. So notice here in a second, it'll let them go. Is there anything below the plane right now? Absolutely not. So let's go. You see them? There they go. And you basically can't see them anymore. But they're still below the plane. So you can see them hit now. So the whole purpose of this video is to show you that even in real life, we're clearly not ignoring air resistance here. They pretty much stay right below the plane. Y'all see that? And so, again, they would still have the same initial velocity as the plane, but they're going to accelerate downward because of gravity. So, if you're going to drop something like supplies, or in this case, bombs, you have to drop them before you get to your target, right? Because they're going to continue to move along with you. If you drop them right when you're on top, well, then it would continue to move along and hit something else, right? So, that's just a little thing there about projectile motion. I'm not going to play that video. You can watch the car versus motorcyclist, but it does beg the question, why is it ill-advised to shoot a gun directly into the air? Well, if bullets are just projectiles, if you fire it straight up, what's going to happen to that bullet? It's going to come straight down. Now, it would actually be really difficult to fire it, exactly straight up. You're probably going to be off a little bit. So when it comes down, it can actually have quite a range in terms of a bullet from a gun because those have quite a large initial speed. But what's interesting is that if they come down and actually hit somebody, which has happened, if let's say you're in your house and all of a sudden you get shot, a bullet comes through your roof and hits you, which doesn't happen that often, but it occasionally happens. What's interesting is if it goes through, two things, two objects, they can actually use that as two points on the parabola, and then they can use math to calculate the parabola. They know the bullet, and they know the gun it was probably fired out of. They can actually use that to calculate the initial velocity and the path of the projectile, and they can actually trace it back to where it was fired from. And cases have happened where people have gotten shot. Some of them got killed, but some of them didn't. Just sitting in their house, they weren't doing anything because some yahoo was just shooting his guns up in the air. Which I like guns, but it's really dumb to just fire them off in the air. And they've gotten arrested and sent to jail because they shot somebody. So don't fire guns randomly in the air. It's a bad idea. So here, this kind of breaks it apart that like if we're using horizontally fired projectiles, we can see like this is the nice parabolic path that it takes, but it's actually a combination of the two things we've already learned. So constant horizontal motion plus vertical motion that's been accelerated by gravity. And that's what gives us our projectile. And by breaking it apart, it actually makes analyzing it pretty easy. So let's go ahead and do this problem here. So what I'm going to do is I'm going to take this particular problem and I'm going to do it on the whiteboard. That way you guys get a good example of how to do this. Then I'll come back and kind of show you exactly how this thing is set up. So right now it tells me that I have a ball that rolls across a 1 meter tall table with a velocity of 0.6 meters per second. How far from the table did the ball land? Or in other words, what is the range? So let's go ahead and do that. So it says that we have a table that is 1 meter tall, and we have a ball that's initially rolling with 0.6 meters per second, and it wants us to find the range. So whenever you start a problem like this, there's a couple of things that you can do. Some things you should definitely do, and one of those things you should definitely do is draw a picture. So we call this our little stair step. So you have like your horizontal surface that you fired it from, then the drop, and wherever it lands down here. So you're going to have your object that's going to come off, and it's going to give us a nice little parabolic curve. So there's basically 4 things that you could know from the beginning, and I could ask you about. So there's your initial velocity in the x direction. There's this vertical height y. There's the x distance or the range. And then time, which I'm going to kind of write out here by itself. And so that's the initial picture I say that you start with. You can always make your own. So now what we need to do is we need to separate x stuff from y stuff. So I'm going to go in super detail here about that. So what I recommend doing is making something like this T chart here. I'm going to do x stuff versus y stuff, right? So I'm going to get super detailed, and I'm going to show you why we can leave some of that stuff out. So for instance, we talked about we could have an initial position and a final position. We can have an initial velocity in the x direction. We can have a final velocity in the x direction. We can have an average velocity in the x direction. And we can have an acceleration. I'll stop doing that. That doesn't even look like an A now. Okay. And then we could have an acceleration in the x direction. Likewise, we could have all of these things in the y direction. So we could have an initial displacement, a final displacement, an initial velocity in the y direction, a final velocity in the y direction, an average velocity in the y direction, and an acceleration in the y direction. Now notice I didn't put time in here because time doesn't have a direction. So time I'm going to kind of write over here to the side or below it. That way we can see that it's for both. Now, I wrote all of these things out. You don't have to do this every time, but I'm writing it out so you guys can see that when I say it's a horizontally fired projectile, how much simpler it makes the problem, okay? And so once you guys see this, I want you guys to remember, take a picture or something, that this is what I want you guys to do to make sure you're simplifying things. So for this particular problem, it said that we have a projectile that rolls off a 1 meter tall table and it's going 0.6 meters per second. So in order to start, we have to establish an origin. So I'm going to go ahead and put my origin right here where we started. Since that's my origin, what's my original distance? What's my x naught? How far has it gone before it starts moving? Well, it hasn't gone anywhere. That's the origin. So it's gone 0 distance. Does that make sense? Likewise, if we're looking in the vertical direction, well, if that's where it started, it hasn't gone anywhere. Okay? Since it hasn't gone anywhere, then we can say that that is 0 as well. So, call that x, that's a y right there. So now x, in this case, would be how far it goes. That's actually what it's asking us to find in this question. Do we know the vertical height here? Well, in this case we do, because it said it's going to go, it's 1 meter off the ground. So let's say that's 1 meter tall. Now what is your initial velocity in the x? Well, it gives us a velocity here, and since it's going on the table horizontally, its velocity would be in that direction. So its initial velocity would be 0.6 meters per second. And indeed, that would be in the x direction. So my initial velocity in the x direction is 0.6 meters per second. Now, what's the initial velocity in the y direction? Well, the initial velocity in the y direction is actually 0. And the reason why this is 0, we'll make that the same color, is because the ball is rolling horizontally. If it's rolling horizontally, it's not moving up and it's not moving down.
If we're only doing horizontal, does that mean it's always going to be 0?
Yes. And so here, the initial velocity in the y direction is always going to be 0. Now, what's interesting here is I have all of these other velocities. Like I have average, Vx, and I have average Vy. Now, in the y direction, we have an acceleration. The acceleration is caused by gravity. So I can actually call this, a sub g, or I can call it 10 meters per second squared, whatever you want to call it. But it's going to be 10 down. So in this case, I'm going to call it down positive, so I don't have to deal with any negative signs. I think everybody's okay with this. But then, what is the acceleration in the x direction? Well, once the ball rolls off the table, there's nothing pushing or pulling it to the left or to the right. It's pulling it up and down, but not to the left or the right. So actually, the acceleration in the x direction is always going to be 0 for projectiles. Not just horizontal projectiles, but just projectiles in general. But remember that my acceleration is my change in velocity. So if there is no change in my x velocity, then 0.6 isn't just my initial, it's my final. It's my average, it's everything, because it doesn't change. Does that make sense? So here, I don't really need to write this 3 times. I can just write Vx is 0.6. Does that make sense? But this is all exactly the same here. Then when we come over here, that might be, that's not going to be true in my y direction because I'm always going to start with 0 initial velocity, but it's going to accelerate downwards. And so we will have a final, and we could have an average, but most of the time I'm never going to ask you for average, so don't worry about that at all. So for this particular problem, we don't know Vy, we don't know time, and we don't know the x range. So let me simplify this a little bit. So if I simplify this, I'm not going to ever ask for average velocity in the y, so don't have to worry about that. As long as you put your origin where you start, your initial position is going to be 0 for both x and y. Right? And then instead of writing all of this like 3 times, I'm just going to call this Vx. And your initial velocity will always be 0 in the y direction. And so when we do that, it actually looks a little bit better. You'll see that? I wanted to address every single one of these things because we have talked about them in the past. But I want you guys to understand that they're all going to be 0 for either the fact that it's a projectile, like acceleration in the x direction is always going to be 0. So we don't have to worry about that, right? So that actually simplifies things quite a bit, right? And we also talked about how our initial velocity in the y direction is going to be 0 because we're using a horizontally fired projectile. If you don't go horizontal, that one's definitely not going to be 0. But for you guys, we're only doing horizontal projectiles, so this makes things a lot easier. But I wanted to address all of those things just so you didn't be like, oh, well, what about this or what about that? So now, if we're trying to find, like this particular problem does ask us to find this range. Okay, so how do we find that? Well, in order to find that, the very first thing we need to do is find the time. Okay. Now, on the notes, it gives you a couple of equations. The easiest way to find it is to actually use an equation I gave you in a previous set of notes. So I'm just going to write it up here. I'm going to write my time equation is the square root of 2y over the acceleration, a sub g, if you will. So you can also write that like the square root of 2y over g. So in this particular case here, y is my height. So this would be 2 times 1 over the acceleration of gravity, which is 10. So this would be 1 meter, this would be 10 meters per second squared. So in order to find the time, all you need is the height. Okay, that's it. So yeah, you take this, you do 2 times 1, which would be 2, and then do 2 divided by 10, which will be 0.2, and then you take the square root of that, so you should get 0.45 essentially seconds. So remember that if an object falls for 1 second, it should travel 5 meters. Okay, about 5 meters. This is only falling for 1 meter, so our time should be less than a second. So that's less than a second, that makes sense. All right. So that's our time. Now we want to find the distance that it traveled. Well, if we want to find the distance that it traveled, we go, okay, cool. How do we find this distance? Well, the very first equation we talked about was our average velocity. In this case, I'll just call it Vx. Was the change in displacement over the change in time. Now, the way it's written in the notes is essentially Vx equals x over t. Because again, if those initial conditions are 0, and our average final, it's all the same. We got to solve for x, so we can throw up our triangle here and say Vx is x over t. In this case, we would be solving for x, so we just cover that up. And we go, okay, x equals Vx times t. So in this case, Vx is the initial velocity of 0.6 meters per second. And then we multiply by our time, which is 0.45 seconds. So then x is whatever that is. So 0.6 times 0.45. So I got about 0.27 essentially meters. So that's how far this would go from here to there. But 0.27 meters. Now this particular problem just asked for that, but I could also ask a question like, okay, what is your y velocity? Like how fast is it going just before it hits the ground? Well, that would essentially be v equals v naught plus at, but v naught is 0, so we just do at. And so in this case, acceleration is 10 meters per second squared, times our time of 0.45 seconds. And so vy would be 4.5 meters per second. Now, for this particular problem, it's just asking us to find the range, so that would be our answer. I just went through that extra step to give you an example of how to find the final velocity. But keep in mind, I can ask many different questions. I could give you the time and just ask for, the range or ask for this. Or I could do just like this one where I just give you a velocity and a height and ask you to find something. I could also do something like, oh, this thing starts rolling off the desk at 0.6. 20 seconds later, what's its x velocity? What's its horizontal velocity? Well, if the horizontal velocity doesn't change, well, it's the same as what I told you initially, right? There's 100 different questions I can give you that have basically the same setup. So again, when you get to these problems today, you need to take the time to read them, right? Some of them are easier than others. So this is, like a fully worked out solution here. If we're looking here, this is essentially what it's talking about. So you see my stair step, and then you can plug stuff in there from this. So it gives us a couple of equations here. So we have Vx equals x over t. Then we have v equals at, which you saw me use. This one right here, you didn't see me use, y equals 0.5 a times t squared. That would be my vertical range. Like if I wanted to figure out how far it fell, I would simply need the time. But I actually used this equation right here, this guy. And remember I used that t equals square root of 2 times y over g. That's this guy, except solve for t, right? So that's a thing we have there. This next problem here, I'll go through this one rather quickly. And I'm not going to go through all of those steps to show you don't need to do that every time. So for example here, it says, okay, we have a ball rolls across a 2 meter tall table and lands 0.75 meters away. How fast was the ball rolling? So how fast is our initial velocity? That's our Vx. So in this problem, we're actually looking for Vx, okay? So here, Vx is our question. Y is going to be the height, so that would be 2 meters. We don't know time, but it does say that it lands 0.75 meters away. Okay. So in order to find Vx, well, it's just simply distance divided by time. We have the horizontal distance right here. So in order to figure out its initial velocity, we just need time. Well, to find time, we just need to know the height. So we can, like I said, rearrange that guy and use the t equals the square root of 2y. It's called a sub g. So in this case, this would be the square root of 2 times 2 meters over 10 per second squared. So the t, in this case, is it less than 5 meters that it's falling? Yes, it's less than 5 meters. So we end up with we should end up with a number less than 1 second again. But if you remember the last problem, we only went 1 meter, so it should be less than 1, but more than the time from before. And indeed it is. It's 0.63 seconds. There. So now we have the time and the range, so we want to find Vx. So we use this formula right here. And just change the color here. So Vx equals x over t. In this case, x is 0.75 and t is 0.63. And so we get a velocity of something. 1.12, no. I was that completely wrong. Let's just say 1.19 or 1.2, however you will see. And so that would be how fast this object is rolling. So when you're working through these notes or looking at them on your own, it has the answers for these things, not written on the sheet, but for instance, this is the last slide here. So if I click out of this, So it has the answers written down here, like in the notes section. So you can always check yourself. So that's what we got, the notes for today.